Hey guys, we're gonna work through a couple problems here. Um, this is something you would do after you had studied what was in 11.7. Come into this handout here, so it's just a few more problems. So we're gonna take a look. Okay, Charlie has eight different colored marbles. How many different ways can you line them up in a row? Okay, this is a standard factorial problem, counting problem, and we can use the multiplication principle. You just have the 8, 7, 6, 5, 4, 3, 2, 1 situation, otherwise known as 8 factorial. You might note also that it's the same thing as 8 permutations of 8. Okay, taking 8 at a time, 8 things taken 8 at a time. This is your answer, whatever that is. 8 factorial. You can just get that on your calculator. Let's see. I got 4320 like that. Okay. How many different batting orders can a manager of a Little League team make if she has 14 players and has to make a 9-player batting order? Well, there you are again. You've got 14 with 9. Okay, and that one turns out to be, of course, you have your 14 factorial over 14 minus 9 factorial. So that's 14 factorial over 5 factorial. So I'm going to just run through that one. It's a huge number. I'm coming up with 7, 2, 6, 4, 8, 5, 7, 6, 0. Wow, that almost seems like it's too much. I mean, it's huge. I'm gonna check that one more time. It just seems really big. Double check it. That's your answer. 760, 485. Well, it seems like a lot of decisions to make. Uh, I hope running the Little League team isn't that much work, but okay. John has 8 different colored Porsches or Porsches. How many different ways can he line them up single file on his driveway? So again, you've got 8. With 8. Permutations of 8 taken 8 at a time. And you've got the same number, same as number 1. So that was the 40 right there. So you thought having all that money and riches and everything was easy. Look at the decision he has to make here. How to do that, right? Okay. Now he has a problem because he had to downsize, and 5 out of the 8 he can only line up. So he has to pick his best 5 and line them up. So we only have 8 with 5 at a time. Okay. And again, you can do this by hand. 8 factorial. It'll be 8 minus 5 is a 3 factorial, which is 8, 7, 6, 5, 4, which is 6720. So by losing a little money, downsizing, he has less decisions to make here. less choices. How many different words can you form from the letters of the word successfully? Well, successfully. How many letters are there? Count them up first. I see 2, 4, 6, 8, 10, 12. Okay, so we've got 12 factorial. Now that would be if they're all the letters were different. But because of the duplicates, you got to divide them out. You'll have 3 S's and let's see, 2 U's. You got 2 C's and it looks like 2 L's. Okay, so that's some work. Let's just see. I'm going to put this in the calculator. Of course, you know, calculator's only enter so much, but this would be 12 factorial over, it looks like 6 times 8, which is a 48. 12 factorial over 48. I'm going to have the calculator do that for me. Okay, well that is a lot of words. 9979200. Wow, okay. Apple, how many words can we do with that? Well, you've only got 1, 2, 3, 4, 5, and you just have 2 repeats, so this would be 5, 4, 3, and we got rid of the 2 and the 1, so 60. Okay, license plates. 3 different letters, 3 different numbers. So you would have a 26, 25, 24. We're back to the counting, the multiplication principle. We don't need to think, I mean, you could think about it as permutation, but we're still multiplying that by the number. So this is the way to write all of the letters, how many ways you can do that. And you follow that with the digits, which is 10, 9, 8. Okay, see now it's different. That means you can't repeat. So all of those are the number of ways you can write 3 different numbers, 3-digit numbers like that, using the digits from 0 through 9. And all of this is the number of ways you can write those 3 letters. Put them together, and you've got the ways to do these 2 things together. So you can do a little math here. And I'm coming up with 1, 1, 2, 3, 2, 1, 2, 3. It's like about 11 million. Okay. Well, here's an interesting one, number 8. You got to think about this one. I mean, there is one way, if you literally went through and wrote all the numbers, because we're looking at 2-digit even numbers using 1 through 19. So we're really looking at the numbers starting at, 2 digits, not using a 0. So the smallest number we're talking about is 12, because you can't repeat the digits. So that'd be the smallest possible number. And that's going to go all the way to the largest possible number would be a 98. Now, there's lots of numbers in between 12 and 98, and they're not all even. We have to figure out the even ones. And we can't use a number, for instance, like 22, even though it's even, because 22 uses 2 2s. It says that you can't repeat the digits. You can't use the numbers twice. Okay, so you could literally write them all down and then pick out the ones that fit. That's a job. You could also I gave this a little thought. Think about it this way. You have 2 digits. I'm going to go with this. I'm going to think about it as odd and even. Those are the 2 digits for any given number. Digit 1 and digit 2. Digit 1, digit 2. This is the tens place, the ones place. Okay, so let's say you're going to use only odd numbers for your first digit. Well, you have 5 to choose from because you have 1, 3, 5, 7, 9. Okay, so that's the number of ways you can choose your odd digits. Any number that starts with an odd digit. Then you can multiply that by the even digits. Well, you have 4 even digits. You have 4. You have 2, 4, 6, and 8. So that's 4 choices. Okay, now that gives you 20. Now the other way to these 2 digits would be to start with 2 even numbers. Well, to have 2 even numbers. So I did all the odds. Now let's look at the number of even digits that I can begin my numbers. I can start with an even digit. I have 4 to choose from. Okay, start with 2, 4, 6, or 8. And my next digit, I only have 3 left. Okay, I only have 3 left. Well, that's 12 total. You put these together now, that we're going to add these, because this is a number of ways you can start with an odd digit and end with an even. And this is a number of ways you can start with an even digit and end with an even. Notice in both cases they end with even digits, which makes them even numbers. So I have 32 altogether. So this is what makes counting complicated. Now, if you're trying to do this efficiently, that's what makes it complicated. Now, you could use brute force, like I said, and just construct all these numbers. It wouldn't take that long. You know, I mean, you can do it pretty systematically and then pick out the ones that fit the description. Okay, now let's change the problem a little bit and include 0. So this is another interesting twist to the same question. This time, do it the same way. You have digit 1, okay, and you have digit 2. And let's assume, we'll start with the odds now. Again, we'll start with an odd number and we'll end with an even. We have to end with an even. Okay, and then we'll do it again, like we did above, digit 1, digit 2. So we'll have an odd, and then we'll have an, sorry, I meant to say, whoops, where's my eraser? I need my eraser here. Okay, here's, there you go, okay. So this is digit 1, and I start with an even and end with an even. Okay, so, all right, so how many odd numbers do I have to work with? Well, I have 1 through 9, that's 5. And of course, I can end it in an even. Now, 0 is even, okay? And it's included now. So we actually have 5 to work with here. 5 times 5 is 25. So there are going to be 25 even numbers that begin with an odd digit. So we're talking about numbers like 32, 30, 32, 34, etc., 72, 74, those numbers. Over here, we start with an even. Well, we included that 0, but you can't start a 2-digit number with a 0. So you still only have 4 digits to work with. Now, I'm going to multiply that by, what is that? Oh, gosh. Okay, let's get rid of that. No, I want to get rid of that. I said, okay. Disappear. There you go. Okay. Well, let's clean that up a little bit. Okay, we had a little mess up there. Okay. Okay, let's come back here. So we can start, we're starting with even digits. We had 4 to choose from, because you can't start with a 0. You can start 2, 4, 6, or 8. Your second digit, okay, now you're going to use one of the 4, so you got 3, but you're going to add in the other 0, so you still have 4 to work from. You can end with a 0. Okay, so that's 16. We're going to add these. We get 41. 16 and 25 is 41. That's the answer to that question. So this is what makes this stuff fun, if you can call it fun. It's interesting, just to figure ways to get to the bottom. You might try, just out of curiosity, try to do this with 3 digits. Same question using 3 digits, no repeats. 4 digits, try that. Okay. Anyway, let's move on. We're on this one here, spastically. Number 9. Let's bring it down here. How many letters is that? That's 1, 2, 3. I don't know. I can't. It's hard for me to see that. There it is, spastically. So spastically. 2, 4, 6, 8, 10, 11. Okay, so we're going to have 11 factorial. You got to divide out any repeats. There are 2 A's. Are there any A's? There are 2 A's. Okay. I do a little Wheel of Fortune here. Are there any L's? 2 L's. I almost forgot the S's. There are 2 S's there. Okay. And I think that is it. 2 L's. Let's see. So that one now, those are just 2's under there. So really, you've got, this is a pretty big number again. You got 11 factorial over 2, 2, 2 is 8. So that's a job for the old calculator. All right, so we're coming up with 49,896,00. Oh, some huge numbers here. We got huge numbers. All right, let's go back to this one now. I can read that. Okay, that's number 10 now. How many different ways are there to set in a line? 4 red, 1 blue, 1 green, 3 yellow, and 2 orange marbles. Okay, a little room here. Okay, so let's think about what we have here. 4 red. Okay, so we're going to use them all up, right? That's what it looks like. How many different ways are there to line everything up? This is kind of like, like a word, like the above word, but we already see we have 4 repeats of the red, and 3 yellows, 3 repeats of yellow, and 2 repeats of the marbles. It's the same kind of thing if you just think of these marbles as matching letters. We've got 4 reds, so it's a word with all of these things in it. So it's the same reasoning. We're going to take, we got 4, 1 is 5, 6, 7, 8, 9, 10, 11. So we are going to have 11 factorial, and then you got to divide out the matches, because nobody can tell the difference. When you when you line up, let's say you have red, 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 and then you have a blue, one blue, and then you have a green, and then you have 3 yellow, 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 and then you have 2 oranges at the end. Nobody can tell the difference when you start rearranging these. Nobody can tell the difference between those. You can move these 4 R's, these red ones around, leave them in the front here, and move them around. Let them interchange places with each other. Fact is, you have 4 factorial ways to do that, to rearrange these 4 R's, and nobody can tell the difference when you do it, since they're all the same color. So that means rearranging those is not going to help you create new words, new arrangements of these colors. So those have to be divided out. That's only one of them really counts. So you divide that out. That's why we're doing this, why we divide out. Because even if you could keep track of these, put marks on them somehow, they're all still red, so they only count as red marbles, and they're all the same. So, and that's just one simple way to look at this. I mean, we could also have the R's spread out throughout these, and that would be another permutation, which could then be duplicated 4 factorial times just by mixing up the R's again. In other words, you might have an R, blue, green, then an R, and a yellow, yellow, then an R, and a yellow, orange, orange, and an R. So that's 1, 2, 3, 4 R's. That's another grouping. It's unique, but if you change these R's around, you can create another one just by interchanging the R's. That's one of these. Well, that's one of, for this particular arrangement, there are 4 factorial arrangements just like it that you can't tell the difference between them. You can't tell the difference between them. And those are the ones that are being counted if you just look at 11 factorial. So that's one of the 11 factorial, and there are 4 factorial more of those, that same arrangement with the R's the way they are here. And we can't count those because they aren't part of, they're duplicates, they're not different. Okay, so that, we have to do the same thing with the yellow, divide out that 3 factorial, and then the orange, 2 factorial. So that is going to be our so let's see what we got here. This is another one I would just, I'm not going to use, I mean, it isn't that much work. Actually, let's take a look at this. If you, let's expand this a little bit. 11, 10, 9, 8, 7, 6, 5. And I can leave that 4 factorial there because I have a 4 factorial here. And that 3 factorial is just a 6, and then you got a 2 there. So the 4 factorials divide, the 6 divides, the 2 can be divided into that 8 is 4. So I'm going to have is 11 times 10 times 9 times 4 times 7 times 5. That's not too bad. You can do that on the calculator. $13,860. Okay, so that's not as large as the 11 factorial. I mean, the 11 factorial is going to be huge. 11 factorial is, just for the record, 39916,800. Okay, that was the 11 factorial. And so we divided out all of those duplicates, and we only got this many different arrangements, that distinguishably different. Okay, so that's a little bit of work there with the finishing up that 11.7. And you know what, I'm going to call it quits right there. And we're just going to put this one out there.